In this video, we're going to be looking at optimization problems. And optimization problems, they're just a fancy way of saying using absolute maximum and minimum values in the world around us. They're basically word problems where we utilize that idea of absolute maximum, absolute minimum. We use those critical numbers in order to solve for the highest value of a particular thing or the lowest value of a particular thing. Okay? So like say, for example, we want to find two positive numbers whose product is 100 and whose sum is a minimum. Okay? What we're going to do is we're going to set up this problem, and you're going to see how this is basically just utilizing our ideas of absolute minimums and absolute maximums, right, in conjunction with some of the work that we did with related rates. So let's find two positive numbers whose product is 100 and whose sum is a minimum. So what we're going to be doing now is we're going to be looking to minimize a function, okay? Which is, again, what we're going to do is we're going to find its derivative, set it equal to 0, and then solve, okay? And that'll give us its minimum. And it may also give us our maximum, depending upon what we're looking at. Now, let's find two positive numbers whose product is 100. So let's choose our numbers. We'll call our numbers x and y, all right? And let's consider that they have to both be positive. So x and y must be greater than or equal to 0. Or excuse me, not greater than or equal to, but just simply greater than 0. Okay? And what we know is x times y, and so that's because they're positive. X times y will equal 100, right? And we want to minimize their sum. Okay? So what we're going to do is we're going to find a function of x and y for their sum. And that's fairly simple. That's going to be s equals x plus y. That's their sum. Now what you'll notice is that s is in terms of both x and y. What we want to do is we actually want to eliminate one of those variables utilizing the other function. Okay? That way what we get, much like the related rate problems, is we get a single dependent variable in terms of a single independent variable. So now I'm going to let y equal 100 over x. So s, my sum, is going to equal x plus 100 over x. I'm going to do a little simplification here, and I'm going to combine my like terms, and I'll end up with x squared plus 100 over x is what s is. Now, to minimize, I'm going to find ds dx. Okay, so we don't have to actually do any implicit differentiation this time. I'm going to find ds dx, and I'm going to set it equal to 0. Okay, we'll set it equal to 0. So we have that s is x squared plus 100 over x. So I'll let f of x equal x squared plus 100. And I'll have f prime of x equal 2x. Then I'll have g of x equal x, and g prime of x equal 1, because we're going to be utilizing the quotient rule. So what that gives me is, it'll give me 2x times x, this is going to be s prime of x, minus x times x squared plus 100 divided by x squared. This will then equal, right, this is going to be 2x squared minus, and this will be x squared minus 100 divided by x squared. So this ends up being equal to x squared minus 100 over x squared. And now what I want to do is I want to set that equal to 0. So that's going to be x squared minus 100 divided by x squared equals 0. Since the bottom, the denominator, can't equal 0, we know that the top has to be what's equal to 0. So we're going to take this and we're going to say x squared minus 100 equals 0. So that means that x minus 10 times x plus 10 will equal 0. So in this case, for this equation, x equals 10 or negative 10. Now what we want to notice is remember our domain. Remember our domain? So since x and y have to be greater than 0, x cannot equal negative 10, so x has to equal 10. Then all I've got to do is plug in for y. Y equals 100 divided by x, so 100 divided by 10. Okay, that's coming up from up here. And so that equals 10. And so those are our two numbers. X equals 10 and y equals 10. Just to review, what did we do? Well, we had two equations, right? One equation actually had both of our independent variables in terms of some value that is known. Okay? We're going to use that later on in order to solve for one of the variables. The second one is the function that I want to minimize. So this is what I want to minimize. Okay? And what we notice is that that's in terms of two variables. So what I'm going to have to do is I'm going to have to substitute, utilizing the first equation, okay, into the second equation. Once I've done that, then it's a matter of taking its derivative, setting it equal to 0, and then solving. Don't forget to go back up to your question and take a look at what it's actually asking for so that you can make sure that you're actually solving for everything that the question is asking for, right? We always want to like reinterpret in terms of the question or in terms of what we've been asked, all right? So don't always just stop with, oh, I set it equal to 0 and I found what x is. Well, don't forget that you may also have to find what y is. Now let's take a look at this question. What is the minimum vertical distance between the parabolas y equals x squared plus 1 and y equals x minus x squared? Okay, now in this case, I kind of want to draw a graph in order to visualize this a little bit. My first parabola, x squared plus 1, looks like this. And my second parabola, x minus x squared, is going to be facing downward, and it actually has its vertex at 1/2. Okay, so it looks something like this. And when we talk about vertical distance, okay, the vertical distance is the distance on the y-axis, okay, because it's vertical. It's a vertical distance. So basically, we can think of here, this, we'll call this y1, and this one here y2, okay? And so it's basically, or we'll make the top one y2 and bottom one y1. It's going to essentially be y2 minus y1. So we kind of want to just be able to visualize what it is that the question is actually asking us for, okay? Well, if that's the case, then I'll make the top one, right? Because this one's x squared plus 1, and this one is x minus x squared. I'm going to make the top one into y2, so this will be my y2, and my bottom one will be y1. So now the distance between the two of them is going to be that equation right there, okay? So in this case, we're not going to actually have to do any substitution. Instead, what we're going to have to do is we're just going to have to do some visualization so that we can, in fact, do this problem. So this is going to be d equals x squared plus 1 minus x squared. And this is going to end up being x squared plus 1 minus x plus x squared. Okay, so d will end up equaling 2x squared minus x plus 1. And there we go. Now what do I want to do? Well, I'm looking to find the minimum vertical distance, so the smallest vertical distance between the two. So I'm going to have to find d prime. So d prime is going to equal 4x minus 1, and then I'll set d prime equal to 0. 4x minus 1 equals 0. So what we get is 4x equals 1, and then that gives me that x equals 1/4. Okay, so that's the value of x. Very important that that's not actually the distance. This is asking for the minimum vertical distance. So what I'm going to do is I'm now going to plug that back into d. I'm going to find d of 1/4. So d of 1/4 is going to be 2 times 1/4 squared minus 1/4 plus 1. Okay, and that'll end up equaling 7/8. So 7/8 is our minimum distance. Once again, the challenge here and then what takes practice is actually finding the formula. Okay, once you found the formula, then finding the minimum distance is a matter of taking the derivative, or the maximum distance. It's taking the minimum distance in this case is taking the derivative and then setting it equal to 0 and then solving, and then making sure to go back to your problem, check what the problem is asking, and utilize the information that you have in order to solve that problem. All right, so that's an introduction to optimization problems. All right, there are a lot of different varieties. They utilize a lot of different formulas. You may be looking at formulas, maybe like kind of reading inside the book to see some examples, or coming back into class and asking about examples. Totally natural, something that you should definitely be doing. We're going to be working on these quite a bit. All right, so this ends the lesson.